Hello, we're going to work through solutions to the problems assigned out of section 4.5. First up is solve the following inequality regarding a polynomial. So the basic thing to remember when solving these polynomial and rational inequalities is that positive numbers multiplied or divided by positive numbers are positive, a positive times or divided by a negative is negative, and a negative times or divided by a negative is positive. That's really all there is to it. So here's why that's all we really have to do. So this polynomial has already been factored for us. So we know if x is less than minus 6, then x plus 6 is negative, but then x plus 6 squared is positive. If x equals minus 6, then x plus 6 equals 0, in which case x plus 6 squared equals 0. And if x is bigger than minus 6, then x plus 6 is positive, in which case x plus 6 squared is also positive. So observe, if x is less than minus 6, then x plus 6, squared is positive. If x is bigger than minus 6, then x plus 6 squared is positive. But if x is equal to minus 6, then x plus 6 is squared is equal to 0. Very similarly, if x is less than 5, then x minus 5 is negative. If x equals 5, then x minus 5 equals 0, x. And if x is bigger than 5, then x minus 5 is positive. So overall, all we really have to do is draw a number line. This is my preferred approach to this, with all of the zeros of the various factors marked off. Negative 6 is a 0 of one of the factors, and 5 is a 0 of one of the factors. Okay, so for x less than minus 6, the first factor was negative, but it's being squared. And then if x is less than minus 6, that third factor is negative. At x equals minus 6, we end up with a 0 squared times a negative. I'm just using pluses or minus in parentheses to denote whether the number is positive or negative. And I like to distinguish in between points versus at points with above or below the real number line like this. So in between negative 6 and 5, x plus 6 is now positive, it's being squared, but x minus 5 is still negative. At x equals 5, x plus 6 is positive. I mean, it happens to be exactly 11, but that's fine. And x minus 5 is equal to 0. And for x larger than 5, the first term is positive, it is squared, the third term is positive. So now overall, we can now answer the question, where is the polynomial positive versus negative versus 0? So to the left of minus 6, I have negative squared times negative. So negative times negative times negative. Overall, that is negative. Here I am equal to 0 because one of the factors equals 0. And also at x equals 5, one of the factors is equal to 0, so the result is 0. In between 6 and 5, we have a positive number squared times a negative number. A positive number squared times a negative number, so the result is still negative. And finally, when x is bigger than 5, I have a positive number squared times a positive number. That result is positive. And now we can, just by looking at this picture, answer the question, where is the product x plus 6 squared times x minus 5 negative? So from looking at the picture, it is to the left of minus 6, but not at minus 6. At minus 6, this resulted in a 0. And then in between negative 6 and 5, but then not at 5, and not anything bigger than 5. For all x is bigger than 5, the resulting product was positive. So the end result is everything up to negative 6, but not including negative 6, as well as, or union, everything between negative 6 and 5, but not including either one. Okay, so this first interval here accounts for everything to the left of minus 6, but I'm not including negative 6. The reason I'm not including negative 6 is that at x equals minus 6, the result is 0, and in the original problem, I wanted the result to be less than 0. So the way the problem is exactly phrased is going to be quite important. And then I also want everything in between 6 and 5 because the result was negative, but I also don't want 5 because the result would be 0. Okay, so let's move on. So again, I'm going to draw down a number line. I'm going to put all the relevant roots or zeros of the polynomial on the left in here. What's really important is that this is set up as a polynomial which is already factored for us, and I am comparing it to, by which I mean either greater than or less than, etc., to 0. If I wanted to express where is this bigger than 6, I'd be really out of luck, okay? Comparing things to 0 when they're factored is really nice because I can play this very simple game of positive times negative is negative, that's less than 0. Positive times positive is positive, that's bigger than 0. But a negative times a negative could be bigger than 6. Negative 2 times negative 10 is positive 20, that's bigger than 6. Okay? But a positive times a positive might be smaller than 6. 1 times 3 is smaller than 6. This trick really only works when you have an inequality compared to 0. And specifically, that polynomial on the left needs to be factored so that I can easily address which factors are positive and negative on their own. Okay, so the roots here are 1, sorry, I usually put them above, 1, 2, and 9. For x to the left of 1, x minus 1 will be negative, x minus 2 will be negative, and x minus 9 will be negative. At 1, I end up with a 0 overall because the first factor is 0. And at 2, I get 0 because the second factor is 0. And at 9, I get 0 because the third factor is 0. Now, at x equals 1, the second two factors are still going to be negative, but that first factor flips from being positive to negative. How do I know it flips there? Where is x minus 1 positive? Well, that will be x bigger than 1. Where is x minus 1 negative? Well, that will be x less than 1. It changes exactly at 1. Okay. So similarly, x equals 2 is exactly where that middle factor changes. And x equals 9, the third factor changes. Compare this to the last example where there was a factor being squared, which meant that even though the factor itself changed from positive to negative or negative to positive, because it was being squared, that didn't really matter. But here, every factor that changes really gives you a change from positive to negative. And overall, we can just answer a negative times a negative times a negative, that's negative. Here I'm 0. Positive, negative, negative, overall is positive. Positive, positive, negative, overall is negative. And positive, 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 overall is positive. So let's refer to the problem as stated to ask, do I want to include 0 or not? I do. The question was, where is this product bigger than or equal to 0? So we can come back and we can say, where is this bigger than or equal to 0? Everything from 1 to 2, including both of those points. At 1, the result is 0, and at 2, the result is 0, and I wanted to include those. But then also, everything from 9 and above. And we do want to include 9, because at 9, the result was 0. That's why we included 1 and 2 as well. And the problem as stated says, yes, include 0 in this inequality. Notice I never include infinity in an interval. It's not actually a number, so I don't want to indicate that I'm including it in the interval. Okay. Very little changes here, except the denominator hasn't quite been factored for us. But it's just a difference of 2 squares. There are no shared factors to cancel. That's an important thing to check. Okay, but now I do the same thing. I just mark, now that I have a rational function, all factored, and I am comparing it to 0. This symbol is just my generic way of saying either bigger than or less than, some sort of comparison. We're going to do the same thing. Mark down all the zeros of all the factors. Well, I've got a 0 at -1, I've got a 0 at 1, and I've got a 0 at 5. So we're going to play the same game. Okay. the numerator, that x minus 5, is negative until I hit the value of 5, and then it changes to be positive. The denominator, the x plus 1, is negative until minus 1, and then it is going to be positive. And the factor x minus 1 is negative until I hit the value of 1, and then it changes to be positive. So let's not look yet at what happens at the values of 1, negative 1, and 5, but let's look in between. Okay. To the left of minus 1, I have negative squared over negative negative. Overall, that's positive. Here I've got negative squared over positive negative. Overall, that's negative. This is now negative squared over positive positive. Overall, that's positive. And positive squared over positive positive, that's positive. Okay. Really, we're just counting how many minuses do we have. An even quantity, then the result is positive. An odd quantity, then the result is negative. Okay, but now I can't just say, and this would be a very, very common mistake, to say, oh, and still I'm 0 at all of these points. No longer true, okay? Because some of these zeros are occurring in the numerator, but some of them are occurring in the denominator. If the numerator of a fraction is 0, then the result is 0, and that's just fine. But if the numerator is non-zero and the denominator is 0, this simply does not exist. This corresponds to a vertical asymptote. Assuming the rational function was already factored and had common factors canceled out. So at x equals minus 1, this is a vertical asymptote. At x equals 1, this is also a vertical asymptote. At x equals 5, the result is 0. Okay, because that value, x equals 5, is where the numerator equals 0, and that's okay. So overall, we can now answer the question, where is the original rational function bigger than or equal to 0? Well, everything up to minus 1, but not including it, because x equals minus 1 was a vertical asymptote. And then everything from 1 to 0, including 0, but not including 1, okay, because 1 is a vertical asymptote, but 5 is not a vertical asymptote. It's simply a 0 of the function. I was saying 0, so I accidentally wrote 0. This was corresponding to x equals 5. And then it also includes everything from 5 and above. Now I would point out that this right here says everything from 1 to 5 and then everything from 5 to infinity and also include 5. So really you can condense that to just be everything from 1 to infinity. Overall, the points that we included were everything to the left of minus 1, but don't include minus 1. Don't include 1, include everything up to 5, and do include 5, and then include everything bigger. So this interval right here, I just wrote as the interval from 1 to infinity. Okay, let's move on and do more. So we have a rational function. It's being compared to 0, and it is already factored. So we just jump right into it, and I need to put down all of the roots of the various factors. So in the numerator, I've got a root of 0, -6, and 8, and the denominator, -3 and 4. I'm just writing them out in advance when there's a good number of them so I can put them in the proper order. -6, -3, 0, 4, 8. I'm not really trying to draw this to scale. Scale doesn't matter here. So let's just take a look at what happens. Okay. So that first factor of x squared, when x is negative, that's a negative number squared. Why don't I use a different color? That will be a little easier to keep track. So I've got a negative quantity squared until I hit 0, then that changes to a positive quantity squared. Now let's take a look at 6 plus x. That flips at -6. So here that's going to be negative, but now it has changed to be positive. I like to go through factor by factor. The factor of x minus 8 changes at x equals 8. Okay. The factor x plus 3 changes at x equals minus 3. And finally, the factor of x minus 4 changes at x equals 4. And now we can go through and count how many minus signs. Okay, so I have, in this first bit, I have 2 of them because it's being squared, 3, 4, 5, 6 of them, so overall that's positive. Here I'm going to have 2 of them, 3, 4, 5, so the result will be negative. 2, 3, 4, positive. 2 of them, positive. 1 of them, negative. None of them, positive. So we just go through and mark all that in. So this was overall positive, negative, positive, positive, negative, positive. And now let's address what happens at each one of those special values of negative 6, negative 3, 0, 4, and 8. The zeros of the numerator result in a 0 overall, but the zeros of the denominator result in vertical asymptotes. So where did I get something bigger than or equal to 0? Here, but also including there. Here, but including there, but also including here and here. So I can condense this as everything up to negative 6 and not including it, everything from minus 3, which I'm not including, to 0, including 0, and then going all the way to 4, but not including 4, and then everything from 8 onward, and I do want to include 8, but not infinity. And there we have it.